In this video, I'd like to talk about some of the details regarding the force of friction. If you remember the force of friction, it was first introduced with a slide definition that looked a lot like this in one of the previous videos. We talk about when two solid objects touch one another, each can experience a force that is parallel to the contact surface. Can being very important in that definition. It doesn't always appear. And in this video, I'd like to talk a little bit about why it does and why it doesn't sometimes. As it says here, the force of friction increases if the surfaces are pressed together and decreases if they're not. So that means that the force of friction is proportional to the normal force. That's what that is when we talk about the force between the two objects when they're pressed together. That's the normal force. So you might start out by saying that the force of friction is equal to the force normal times some coefficient. And our equation is actually going to look a lot like this, but don't write that one down just yet. I'm going to need to elaborate on friction a little bit more. First, that coefficient mu. Mu is the coefficient of friction, and if you're asked to use the coefficient of friction, you would want to look it up in table 5.1 in OpenStax, or it might be given to you in a question. For example, on the test, it would probably be given to you. But in general, it's a measure of how rough the two surfaces are. So if you talk about something like metal on wet ice, your coefficient of friction would be very close to 0. But you need both surfaces. Metal by itself doesn't have a coefficient of friction. You have to know what it's on. So for example, metal on dry concrete would have a much higher coefficient of friction than metal on wet ice. Let's take a look at when friction would appear and when it would not. If two surfaces are in contact with each other and they're not sliding across one another, then whether or not there is friction depends on what other forces are applied. So let's imagine we have this skier on waxed wooden skis standing on some sort of snowy or icy patch, and they're just standing there stationary. What forces would we see, would we want to include in our free body diagram? Well, we know the Earth is pulling down gravitationally on the skier, so we would start off with the force of gravity. And we also know that the skier is being held up by the ground, so there's a contact force, a normal force, with the ground. If the skier is just standing there, that's all we would have. Now I want you to imagine that the skier is struggling to move to the right, but we don't see them going anywhere. So we can refer to whatever they're doing with their struggle as maybe a pushing force. And if they're not going anywhere, then that looks a lot like a free body diagram that would have an object accelerating to the right, and that doesn't match up with the idea that they're not going anywhere. When two objects are in contact but they're not sliding across one another, you always want to ask yourself, is there a force in this question that would accelerate one of these objects if the surfaces were frictionless? If the answer is no, then in that particular question there's no friction and you're not going to want to introduce it. But in a situation like this one, yes, these two, the skier would slide across the ground. So if they're not actually sliding across the ground, that implies that there's a force of friction here. In fact, it's what we call static friction. Static friction means that the object is stationary. Okay, now I want you to imagine that the skier is struggling harder to move. That gives us a bigger push force, but we still don't see them go anywhere, so what does that imply about friction? It's also larger than it had been earlier. The friction equation says that friction is proportional to the force normal, and it does not in the equation say that the friction force is proportional to some pushing force. In this problem, the normal force didn't change, but the pushing force did. So we were able to reason that the friction force must also have been larger. This is why I said don't write down the equation earlier. There's definitely more going on. The friction force is more than just proportional to the normal force. Something else must be happening related to the pushing force. This is what the equation for static friction actually looks like. And this equation doesn't actually calculate the magnitude of static friction for your particular problem. It calculates the maximum that the static friction could be. How big is the force of friction in your particular problem? Well, if the object is stationary, not moving, then you know that the net force on that object is 0. So then the static friction is however big it needs to be to make that happen. Let's say you calculate how big the normal force is and you multiply it by this coefficient mu, you get this particular value. But if the skier isn't struggling and there's no force push, then you wouldn't want to include that force of friction that you just calculated on the free body diagram. You would actually take it off the free body diagram entirely. So this equation, this inequality that is on the screen right now, it gives you the maximum value static friction can be, and how big it is in a given problem is whatever value between 0 and the maximum static friction that would be necessary to make the net force on your object 0 and keep the object stationary, 0 velocity. But let me go back to this image. What if the pushing force is bigger than the maximum value that static friction can be? You calculate the maximum static friction force to be some value, and the pushing force exceeds that. That means that static friction will lose to the pushing force, and the object can move. That means that the object is no longer stationary, and it's not static friction anymore. We switch over to something called kinetic friction. Please notice the friction arrow on the free body diagram right now. As I switch over to kinetic friction, it becomes smaller. That's because the kinetic friction between two surfaces is always smaller than the maximum that the static friction could be between those two surfaces. And this is the equation for kinetic friction. The force of kinetic friction is much more simple to deal with than the force of static friction, because you might be told in a problem, for example, that an object is moving. And once you're told that, you don't have to worry about static friction at all. You know the object's moving. It has kinetic friction. Kinetic friction is equal to, there's no less than or equal to involved, it's just equal to the coefficient of kinetic friction times the normal force. So the only confusion would come up if you don't know if an object is moving and you have to figure it out in the problem. I'll do one of those in the example video and you can see how we deal with that. Because any two surfaces against each other have both a coefficient of static friction and a coefficient of kinetic friction, you're going to want to be careful when looking them up in a table. Coefficient of kinetic friction will always be slightly lower than the coefficient of static friction, and as you look down here, if you, for example, have waxed wood on wet snow and your skier is moving and you look up the static friction coefficient in 0.14 and put that in, that's not correct. If the skier is moving, then you need the coefficient of kinetic friction. It's not too hard to keep track of. And again, we'll see some of that in the example problems. That's it for this video.